I wish really to thank the organizer for the invitation. They are taking a big risk because it's my first talk on this topic. So especially, you know, I am a quantum physicist. I spent the last 20 years mostly in foundation of quantum theory and quantum field theory. And in the past, I was working on quantum information. There is a huge connection between these two things and the talk of today. And actually, I got involved with the problem of consciousness more seriously, not just as a divertissement, by Federico Faggin and his team, of which Chetan Prakash and Robert Pretner are members. And you know, I got involved. Found at the beginning I was thinking that it's very hard to say something with a scientific method in a serious way. Instead, I changed my mind. So we can connect science is a connection of assumptions and things that you know, things that you believe with consequences. Logical connection. So what matters is that the methodology from the assumption to the last conclusion is correct. So in fact, what we are going to do, we are going to consider hypotheses, heuristic hypotheses, hypotheses that are almost self-evident, and see all the consequences and all the connections, and maybe all the results are trivial. Actually, at the end, to me, most of them look trivial, but they were not trivial before. So maybe you like them. And let's see, what is the next transparencies? I just noticed this morning that there is an answer to all of the 3 questions posed in the 3 meetings. So maybe you don't share the answer, you don't agree. But I would love to discuss about these things. So, you know, information is really everywhere. There is a lot of information in this room now. So there is light shining on the object, coming to my eyes, going to the retina, to the optical nerve, and up to the neuron. And then, at the end of the story, I see something. I see something which has been illuminated by light. So the idea is that consciousness, this is, I hope you agree, is by definition the direct experience of this final information. So it is the most direct fruition of a very structured kind of information, which is manifesting through different types of qualia, color, sound, taste, smell, touch, somatosensation, pain, pleasure, sadness, happiness. And so the starting point is pretty obvious to me. I hope you will share it, because this is the real starting point, is that awareness is a kind of information, and that is the feeling of the information processing that the system has. So if you are the system, like your mind is the system, is a set of qubits, whatever, and we're going to tell what is it. You feel the information because you are the system. What does it mean to have the information? That you feel it. So that's the starting point. So awareness is being the system. The definition of system actually is a precise mathematical definition that we are going to give soon. And the aware system is made of many subsystems. So, for example, many qubits, not just one, many. The point is that this set of systems must be in a coherent state. What does it mean? It means that the state is really pure. That to somebody sounds strange, because we have to be careful. We are not confusing the state of my mind with the mathematical description of my state that I don't know. I have to do measurements, whatever, but I feel the state. I possess the state. Does not mean that I'm able to describe it, right? And this actually, if we assume that, so we have, for the first time, a good reason to say that the quantum state, if you assume that the information, the special kind of information that makes qualia is quantum, this is going to be the assumption, and I think we will put it here, then we have an ontological meaning which is really meaningful for the state, for the quantum state. Otherwise, the quantum state is only epistemic. Is the state that I would describe with mathematics, it would be a mixed state generally. So with some probability, some pure state, with some other probability, some other pure state. So we will make this assumption that awareness is quantum. There will be motivation for this, but we will come back later. And so the point is that this assumption looks so trivial, but it is a huge consequence. That it provide, my opinion, maybe for you it's a trivial one, provide an identification of the conscious system. Because if I have a huge set of qubits that are in a pure state, which is entangled generally, now if I take a subset, the state is not pure anymore. The state of the subset is not defined, is not pure, cannot be pure. So a subsystem of myself is not conscious. I need the whole thing, right? And this is something that you cannot do with classical theory. In classical theory, everything is in a pure state, every single bit. So the ontological state in quantum theory, in classical theory, is every bit in a single yes or no, up or down. So let me say Cartesianly, in puro statu ergo sum. Now, so we get to a kind of panpsychism, but it's not a trivial one, the quantum panpsychism. There are entities, maybe in some superconductor, whatever, there may be some consciousness. There are situations in which there may be some consciousness, which is not only for animals, can be also for things, but not that every single bit is conscious. Okay. Now, since awareness is information, I must use information theory to describe it. And by the way, I know that what I'm going to say you think is not true. There is not a single book of information theory, ever. Because there is this confusion. We identify information theory with the Shannon theory of communication, which is address only the problem of communication. Information is also processing of information, which is something which came out recently through the quantum information. Because we knew only the classical processing, this means algorithms. So you find books on algorithms. But the theory of information is something which goes beyond classical information. And the right approach, the right framework is that of operational probabilistic theory. And I want to make a short review of operational probabilistic theories because I think they generalize and they are more general and more mathematically well defined than Tononi IIT. So what is the idea at the basis of operational probabilistic theory? Is that you have a joint event, which is made of events D, events H, G, F, E. And you have the set of events, which is not just giving to you the joint probability of all of them, but the joint probability depends also on a graph, which is a unidirected graph, a graph of connections between events, like D, C, and which means, and by the way, let me say that each event is one element of a complete set of possible events that can occur, which is what we call test. The point is that if I take the marginal probability distribution of a subset of events, generally this will depend on the graph, also on the marginalized part. So I marginalize, so I sum over all D, over all G, over all C. Then the probability of these three events still depends on these connections, even though I marginalized. This is the point. And I give you an example. So, for example, let me say, this is actually one thing that is going to be axiomatized. If I have two graphs that are disconnected, so the graph is made of two components disconnected, then if I marginalize, the probability is the product of probability. So there will be no connection in the sense that there will be probabilistically independent. So this is part of the axiomatization, just to give you an idea of something simple about this notion. And now, for example, consider these two sets of Stern-Gerlach apparatus. So we have one Stern-Gerlach apparatus on the left and one on the right. And we can change the setup of the left and we can change the setup of the right by making the gradient horizontal or vertical. You see here the probability distribution of the right depends on the setup of the left. Because, so this is the marginal probability distribution of the right. We can see that here is up, here is down, when here we have a vertical and here we have horizontal. Vice versa, instead, the marginal probability distribution of this one does not depend on this one. No? And so what we say, okay, there is a wave or a spin or a particle which is flying between the two apparatus, right? But that's a theory because we cannot see the particle, we cannot see the wave, we just see the clicks of the detector. So essentially the idea is that what we do, we connect objective things that happens, event, and devise a theory of such connection. Actually, if you think about, this is the general method that we should use to make science. We have objective data and we want to explain. So first meaning of explaining is connect them, right? And then to make prediction for future occurrence, namely we want to predict the joint probability of events depending on the connection. This will be the theory. And which events happen is an objective thing. So the event is something that everybody agrees. Whereas systems are theoretical. Maybe you don't agree with this quantum, you say it's classical. The theory is not objective. And this is what Bohr was saying all the time. Poor Bohr, he didn't have the mathematical instrument to say these things, but it was much light years in advance than many other people, including Einstein. And so the OPT is the operational probabilistic theory is methodologically fit because it makes very clear what is objective and what is theoretical, and so is falsification ready. Where most of the time, scientists, theoretical physicists, everywhere, they confuse what is real and what is theory. They take theory as real, which is realism, right? In the classical case, you can do that. In the quantum case, you cannot do that anymore. This makes a difference also for consciousness. So if you want, I can summarize the goal of science is to provide a mathematical description of systems and events. So I want to describe the events, why they happen, and connect them. And this must be consistent with the composition rules, allowing to evaluate their joint probability distribution depending on the graph of connection. So I need to, if I join probability in the sense that, for example, I marginalize, I also want to be able to connect the corresponding event and to make things coherent. So I can say that information theory, why is an information theory OPT? First of all, we say OPT is methodologically fit. Now, why is an information theory? Because if I take this graph, which is a unidirected graph, and I take it finite because I want to consider just a finite situation, then this is exactly equivalent to a quantum circuit in quantum information because it's a unidirected graph which is bounded. And as you see, there are events that have no wire pending at the input, no input wire, because the systems connect events, not vice versa. So there will be nothing here, and there will be nothing here. And these are special kind of events that we call preparation, the one with no input system, and observation, the one with no output system. And if you think about the quantum circuit is just the run of a program. It's not the flow diagram of the program. So you cannot have loops. If you have a loop in the program, then the loop finish. There will be a sequence of many parts of that are the same in the run. So that's why is an information theory. So it is a very general framework. For example, you can compare with just the causal connection. Here we have a description of the system which is much more thorough than just the causal connection. It implies also causal connection, but not only causal connection. And I think is also mathematically formalized differently from the Tononi IIT, which seems to me empirical mostly. And then it provides also what I call a black box device-independent approach by which you can describe things happening without knowing what is inside the boxes that are the events, just giving a mathematical description. So now I want to get rid of all details of the events and just look at their probability distribution. What I do, I introduce equivalence classes of events which occur with the same joint probability in all possible closed circuits. I need to consider just circuits with one component. I don't need to consider circuit with 2, 3 components. So I get rid of all the baggage which is not probabilistic. That is red, blue, whatever. Then I call the equivalence class, the probabilistic equivalence class transformation, and I call state the equivalence class of preparation and effect the equivalence class of observations. And the connectivity rules are ruled by category theory, we will see just very shortly, and the transformation corresponds to the morphism, and the systems corresponds to objects. Let's see. So, so the sequential composition of events will be a new event from system A to system C. This is now becomes a black box that contains 2 events that were more refined description. And as you see, if they are morphism, associativity is automatic, right? Because they are morphism. And you have the identity, and you have, which depends on the system, as exactly as in category theory. Now I want to make composition in parallel. So it means that I define the composition in parallel in such a way that I use this tensor product symbol, but it's not a tensor product in general, depending on the theory. In quantum theory and classical theory, it is a tensor product, but in general it's not. This corresponds to compose also the systems AC in a new system AC, and the system B and D in the system BD. And everything else, I think, is self-explanatory right here. So the probability space will be the Cartesian product of the 2 probability space and so on. Now, generally, the system AB is isomorphic mathematically, so the mathematical description will be an isomorphic structure to that corresponding to BA. Let me call SAB the swap of AB into BA, and I design the swap with this symbol. And we say that the theory is symmetric, the category theory is symmetric if the swap is an involution. And there is to be considered this naturalness condition, that if I move the events along the wires on the swap, they move physically like this. So this commutation between the swap and two boxes, two events, this is called naturalness. And then I have to introduce an identity system because I want to compose preparation with transformations. Preparation I have no input system. Instead of saying there is no input system, I say there is the trivial input system, which makes the composition trivial. Namely, if I have AI and IA, this is isomorphic to A. I didn't write it here. So there is something which works like an identity in the composition, because if I compose a preparation with a transformation, there will be one input only and two output that compose, right? And then I ask associativity. It can be two different kind of situations in which the associativity is an identification of systems or just as an isomorphism. In this case, the category theory will be called monoidal. In this case, it will be called strictly monoidal. And the category theory will be called braided because it satisfies this naturalness condition. Now, the case of the OPT is strictly monoidal braided category. So the OPT is a strictly monoidal category. So I just gave you the framework of what is an OPT. And the case of quantum theory is that it's also a symmetric. So the swap is an involution. And when you build up really a new theory, like for example, PR boxes or fermionic quantum theory or other new invented theory to see if it makes sense, you have to really check associativity, which is the most difficult part in terms of using, for those that know category theory, the hexagon rule, the pentagon rule, depending if it's symmetric or not. And there is another naturalness condition, is that the parallel composition commute with the sequential composition, which implies that if you put here identities and you draw the identity like just the wire without anything, you can move the transformations along the wires. This is useful, for example, to build up a foliation over the circuit, for example, which is not interesting for us now. And then you can always think that a box can be made by other box inside. There will be a coarser or a finer description. You can have wiring in 3 dimensions. You can have wiring in 4 dimensions, because 1 dimension is always the input-output one, so is it like time. And then you can make a field theory description of your box. Like, for example, here, intuitively you understand it's an infinite homogeneous network. Okay, now quantum theory is an OPT. But when I say quantum theory, I don't mean quantum mechanics. There is no mechanical connotation. I mean quantum theory of qubits, as you want, call as you like. Just the rules of the game, which must apply for every system. Like, for example, they should apply for gravity, and we still don't know. The mechanics, actually, we want to derive it from other principle, and this is what we do. But let me say, so quantum theory, now I can, if I derive the theory, means that I have the mathematical description of the system composition, and of transformation. Everything else is a special case of this. So the states will be a transformation from the trivial system to the non-trivial one. So, and what is the mathematical description of quantum theory? It's just that the system is associated to a Hilbert space. The system composition corresponds to the tensor product of Hilbert spaces of the system. And the transformations from system A to system B are completely positive map, trace non-increasing. If you want to say also for the more general case, which is infinite dimensional, but this derivation that we did from principle is only for finite dimension, is trace non-increasing completely positive map from trace class operators over Hilbert space HA to trace class operators over Hilbert space HB. So what is the trivial system? Is the one associated with Hilbert space, which is C, because the tensor product is trivial in this case. And then deterministic transformation are the trace preserving. The states are transformation from positive numbers to positive operators that are positive operators. And then you have the effects that are equivalent classes of observation are positive functionals that can be written in terms of partial trace with a positive operator, which is bounded by the identity. So all these are consequences of this. You see, the theory is completely coherent mathematically and complete without the need of using in a mathematical axiomatization that we derive as theorem from a principle that I'm going to tell you, without using unitary in the postulates. Unitary transformations or von Neumann. Unitary transformation and von Neumann transformation are just special cases of this one. The fact that you can achieve every transformation as a sequence of a unitary interaction with some system and the von Neumann measurement on that system does not mean that this exists really. Indeed, it is not unique, neither the unitary nor the additional system interacting with the unitary, so it's not falsifiable. So is an assumption, is an axiom, which is not good because it's not falsifiable, the axiom itself, and it is not unique, the achievement of the axiom. So, but if you think about just the many-word interpretation, is an interpretation of this additional thing which is not falsifiable. So there is no von Neumann. If we want, we should derive von Neumann in another way, but it's not, the ontology of von Neumann is not falsifiable. The ontology of unitary is not falsifiable. You say, okay, but the transformations are indeed unitary because there is the Schrödinger equation. That's true in the non-relativistic theory, is true in quantum field theory, the free quantum field theory, but if you go to an interacting one, you have the path integral, and in the case, which is not really a well-defined unitary, and in the case of non-abelian gauge theories, you need to introduce, to write the path integral, you need to introduce, to fix the gauge, the Faddeev-Popov ghosts that are by definition not falsifiable because they are ghosts. So there is, but everybody continued with the axiomatization of von Neumann, which is historical, and von Neumann itself was laughing with his own axiomatization. So this is important, I think, because many people working on consciousness start from the fact that we have the postulate of von Neumann, the state reduction is the act of creation of the result which comes from my mind. And this is something which is not really a good starting point, in my opinion. Anyway, so we derive quantum theory from principles that I'm not going to tell because I would need too much time. Let me check the time, sorry. Oh my. So let's go to, So we derived also quantum field theory, the free quantum field theory, by adding additional principles that are, all of them are simplicity principle of the quantum information algorithm, like locality, which means that so we consider a denumberable set of quantum systems. So instead of having the ontology of the field is made of quantum systems, right? We assume that these quantum systems are interacting with interactions that are local, means that each one interacts with a finite number of systems, homogeneous, namely the same everywhere, isotropic, unitary. This is the easiest transformation. And linear, then we get from this assumption a quantum walk on a Cayley graph of a group. We take this group, the easiest one, which is the abelian group with 1 generator, 2 generator, 3 generator, 4 dimension 2, which is the smallest non-trivial dimension. And what we get, in few words, we get free quantum field theory. So Dirac, Maxwell, Weil. Anyway, I'm not going to tell, there are many interesting things here which are, anyway, are not related to our problem. This is the realization of the quantum walk in 3 dimensions projected to show the Dirac particle, which is a Gaussian preparation of the quantum walk, which moves exactly like a particle. So the mechanics comes out from simplicity of the algorithm. Anyway, so we have seen physics comes out as information. Now, if we put together physics and panpsychism, and we have an interpretation of physics in terms of interpretation of information in terms of awareness, then we have a way to say that awareness is fundamental, right? Because fields are fundamental. And anyway, this is just a joke, philosophical joke. Maybe we can discuss that. But let's see other more interesting things about awareness. So awareness, nobody can discuss, is private. So it's a private experience. I cannot share my experience exactly like it is. You cannot read the thoughts. Let's suppose that it's really not shareable in principle. If it's really not shareable in principle, then it must satisfy no information without disturbance. Means that if I try to get some information from your system, from your mind, then I must change something in such a way that if I try to get other information or somebody else try to have the other information, the additional information or whatever, then it will get the wrong one. Otherwise, I will copy piece by piece. So the information without disturbance, there is a theorem which we recently derived for all OPTs, says that awareness is non-classical. So if you satisfy the no information without disturbance, there must be, this is true for every OPT apart from the classical one. So it cannot be classical information. Now, can be non-classical means can be anything, any OPT, which people call post-quantum. Let's say, then what about to consider quantum? Since the physics is quantum, right? So, but maybe we can address some more general kind of information in the future years. Which are the consequences? First consequence that I said is that the personal identity is more defined, because if I take the state must be pure, then if I take the local state of an entangled one is not pure anymore. So a portion of the conscious agent is not an agent. But also the dynamics of this information must preserve purity. So what is the most general trace non-increasing transformation that preserves purity? Is a transformation with one Krauss element, which is probabilistic, which, if you think about, is the generalization of von Neumann-Luders. Von Neumann-Luders is a projection on a larger Hilbert space instead of a dimension 1. And here there is something more. There's just an operator. So an operator on a support is something which is a projection and something more general than an isometry after that. So the qubits that are involved in the consciousness are changing. They are not always the same. They are moved by this isometry or by this operator which has input space different from outer space. They're moved. But they preserve purity. And now, but we see that all communication that we do and every external manifestation of our awareness is classical. So everything outside our mind is classical. So we have this situation that we need to have both quantum and classical, so in a kind of hybrid theory. And if we transform quantum information into classical one when we communicate, clearly we can transmit only a complementary side of the quantum information. We cannot transmit all the complementary aspects, but only one of them. So we have a kind of incommunicability. And on the other side, if somebody transmits to me classical information, I transform into quantum information, I'm adding, in a sense, I'm adding complementary aspects. I'm rotating this information in a kind of Hilbert space and having complementary aspects. So in this way, if you think about, you can, for example, consider a mechanism which is good for free will because it's probabilistic, but it contains also the previous states of my mind, my memory. And it is a reaction to previous information. And now I just want to conclude with the idea that you can try to, I'm saying this is what I want to do with Don Hoffman, which is the cognitive scientist of our team. We can try to propose to a cognitive scientist or a neurologist or to design an experiment to check if awareness is quantum. Why not? So the point is that we don't need to know all details of the functioning of the brain. We just need to have some ingredients, like, for example, two measurements that are incompatible like a measurement of position and momentum, so they cannot be made jointly by definition, let's say. And we must be able to prepare states, especially some kind of states that are, in a sense, again, incompatible. And so for example, the minimum toolbox will be to build for a single qubit, to build up two tests that are incompatible for system A and system B. So we consider two systems that are dimension 2 just to be in the very easiest case. And then if you have two incompatible observations, you can use them as a separating set of observation. What is a separating set of observation? It's a set such that if you have two states, these two states are different if and only if they give different probability on the separating set. So you can discriminate states. And then you can use them to make, once you have a separating set of observation and incompatible observation that are separating set of preparation also, automatically because they are incompatible, what you do, you can make tomography of transformations. You can, because this is a theorem of quantum theory, you can do tomography in this way. in general, for a theory which does not satisfy local discriminability, which is one of the postulates of quantum theory that I showed before, I didn't explain, you need to consider all embedded. But since we have local discriminability in quantum theory, it is sufficient just to consider input-output relations. The more general case, you need to consider a circuit which has a wire also here, a parallel wire to the transformation. But what I want to tell is that it would be great if we can make a proof of the quantumness of awareness. And I'm done, I'm finished. And this is actually something which is not impossible, in my opinion. So you have to provide incompatible observation test, 2 for one system and another 2 for the other system. Like, for example, we want to see a violation of a Clausen-Onsimony-Olt inequality bound. So we need sigma y and sigma x here, and then here, if you use the singlet at 45 degrees. But if we use some different state, it can be the same, right? So the point is we need to prepare an entangled state. So we can assume, for example, that there is entanglement in some kind of input. Like, for example, a stereographic image may be producing entanglement. Maybe the way in which I see a stereographic image is because there is entanglement between information from one eye and the other eye. I don't know. I'm just giving an idea. The point is that, apart from checking that there is no possibility of causal connection between the two, so if there is a distance between the two sides of 3 centimeters, then I should make the measurement sufficiently fast, like a nanosecond, because otherwise there may be communication in principle. But I can say, okay, suppose, I know there is no light transmitted in my brain. So I know that there is no communication for other reason. Then I don't need this. So I don't need this. The point is that the person that, for example, gets 2 different inputs in the eyes, I just give an idea. I have in mind something, but it is something that I have to check with Don Hoffman. If the guy said, I see an image here, I see another image here, randomly, for example, by making some measurement which corresponds to, for example, put another image before. And if the guy say yes or no, here, left or right, with the statistics will violate the Clausen-Orsimony bound, I will have proved non-locality, which is quantum, and then I will have proved that the awareness is quantum. Regardless the functioning of the brain, regardless everything. If I see 2 things that are far, I don't know anything, and I see a statistics which violates the Clausen-Orsimony-Olt, this is a proof of non-locality independently of the functioning, independently on what's going on, which in my opinion would be very interesting. The point is that we will see if we don't get this these statistics, clearly we have not proved anything. Anyway, just to close, thank you very much. This is essentially what I wanted to tell, and there are other things we can say anyway, maybe in the discussion. If you are interested in the derivation of quantum field theory from principles and quantum theory from principle, then you can go to, you can read just one paper, which is a short account of 50 pages just of the software, which is this International Journal of Theoretical Physics I dedicated to David Finkelstein that died 2 years ago. And then maybe we can discuss with this graph of connections in front. Thank you very much. And